Good afternoon and welcome to today's webinar by the Global CCS Institute. Thank you all for joining us. Today's topic will be a presentation on applying the carbon capture and storage technology to a Chinese steel plant. This will be looking at a feasibility study conducted by Toshiba in China. Just to give you a few housekeeping explanations to start off today's webinar. I'll be making some introductory remarks and then handing over to our presenter, Kensuke Suzuki from Toshiba. Following his presentation, we will have plenty of time for your questions and answers. If you'd like to send through a question, please enter it into the box that should be on your screen in the GoToWebinar app. You can send through your questions at any time throughout today's presentation, and I'll be able to ask them to Suzuki-san after his presentation. Could I ask, please, that all questions are in English, and that will make it easier for us on this end. If we don't have time to get to your questions, we'll make sure that we respond to you out of session after today's webinar. So moving on now to introduce today's presenter. Kensuke Suzuki is the CCS Business Manager at the Thermal and Hydro Power Systems and Services Division at Toshiba. Suzuki-san is currently the CCS Business Manager, and in this role he is responsible for the development and deployment of carbon capture and storage for thermal power systems, particularly with a focus on post-combustion carbon capture technologies. But today he's going to be talking to us outside the world of power systems and focusing on post-combustion carbon capture technologies at a steel plant. Suzuki-san holds a bachelor and a master's degree in mechanical engineering from the University of Tokyo. As I mentioned, we're happy to collect your questions during the presentation. I will be able to pose these questions to Suzuki-san after the presentation and submit them in your GoToWebinar control panel. But on that note, I'm now going to hand over to Suzuki-san and ask him to lead on with today's presentation. So thank you very much.
All right. Thank you very much for that kind introduction. My name is Kensuke Suzuki. As introduced, I come from Toshiba Corporation. Today I'd like to talk about on the topic of applying carbon capture and storage to a Chinese steel plant. Today I formulated a 25-page presentation on PowerPoint. Hopefully I would try to go through them so that we can understand what we're doing here. The contents of today's presentation are as follows. First, I would like to talk about what we do in carbon capture and storage arena. And then, of course, go into the background of the project for this particular subject case. And then discuss a little more in detail what we did as in terms of the project planning and evaluation. And then to wrap things up, summary at the end of the presentation. So what we do. As Claire introduced, we, Toshiba, are involved in carbon capture with a focus on thermal power plants. We find that today's thermal power plant market is in, so to say, a challenge as in terms of CO2 reduction. And Toshiba saw carbon capture and storage as being one of the key devices or instruments to decrease the CO2 footprint. However, in going to carbon capture and storage arena, it is not easy as just saying we are in the arena. We needed to be put into the face of the arena. We had originally R&D activity going since 2005, looking at possible amine solutions for post-combustion capture CO2 screening technology. But in 2008, we decided that we need to bridge this R&D effort into a power plant design to particular applications, be it thermal power plants or other things. And in doing so, we needed to demonstrate that this technology works at a certain scale. And this is where our pilot plant, the Mikawa pilot plant, comes into play. Toshiba owns and operates a pilot plant of post-combustion capture technology operating on flue gas in Mikawa. Mikawa is the name of the power plant in the western part of Japan. It is a 47.5 megawatt coal-fired thermal power plant. It is owned by a company called Sigma Power, which is a subsidiary of Toshiba. So virtually speaking, we own this power plant and we sell the power that's coming from this power plant. Toshiba once again constructed a post-combustion capture pilot plant onto this Mikawa thermal power plant to demonstrate and evaluate this technology, and of course, to prove to our customers that this technology works. Next slide. I'm sorry about the busyness of the slide here, but it gives you the overall summary of what we do at the Mikawa pilot plant. So in 2009 September, we constructed and commenced the operation of this post-combustion capture technology. It is still working. It's still operating as I speak here. It captures 10 tons of CO2 per day from a live flue gas of this Mikawa thermal power plant. As it may become relevant at a later stage, we have devised some modifications to the pilot plant that enables us to test the flue gas at a different CO2 concentration, from 4% up to 30%. A natural coal-fired thermal power plant flue gas would usually have around 11 to 13% of CO2 concentrations, but we have devised a recirculation loop on both the exit of the observer and stripper so that we can test these different CO2 concentrations and its effect to the performance of the carbon capture technology to different flue gas streams. Very brief summary of the results of the pilot plant as I speak. More than 8,000 hours of operation on live flue gas. Based on coal-fired thermal power plant flue gas, we have a technology that can go down to 2.4 gigajoules per ton of CO2 at a CO2 recovery. Continuous operation of 2,800 hours plus and so forth. There are some web links that's open on Toshiba's website that's referred on the bottom. If you have time and are interested, please look at these web links. Once again, going back to the topic of the title, which of course may interest all the audience here today, where I'd like to talk about the background of the project, first of all. Global carbon emissions in 2013, as you can see, there are major emitters in the world, starting with China, USA, EU, but as you can see, as of 2013, 28% is from China. And of course, the CO2 issue is a very critical issue in China, and we still find some possibility of a carbon capture storage implementation in China. That is why we're focused in doing something here in China. Primarily, if you look at the graph on the right-hand side, the CO2 emissions is usually inherent to the power sector, 38%, followed by cement and so forth. But still, there is a 15% portion of industrial emissions coming from the steel industry. As always discussed in GCCSI forums, while power CO2 emission abatement can be achieved by introduction of nuclear, renewables, and other non-emitting CO2 sources, energy sources. For steel industries and so forth, industrial sectors, CCS is seen to be a critical option for implementation because there are little other options for reducing CO2 in those sectors. CO2 emissions from the Chinese steel industry. If we look at the trend of CO2 emissions from 2005 up to 2013, though it is somewhat gradually not increasing as rapidly as before, there is still a trend of increase of CO2 from this sector in China. And there are, of course, many iron and steel industry companies in China. We have come into discussion about potential introduction of carbon capture technology with this sixth largest steel industry, the Shogun Group. These are the people who we have engaged to do this feasibility study. I will talk about the arrangement in the next slide. Once again, these graphs tend to be a little complicated, but this just gives you a general idea of why we're doing this in the first place. Of course, NDRC, National Department Reform Commission, who has a very strong political voice in China as to what China does in the policy, has requested the steel industry in general to reduce their CO2 emissions. And while Shogun Jintan Steelworks have been talking with their contacts, they have talked to the Dongfang Environment Company as to an option, seeking an option for reducing CO2 emissions. And that is the reason why Toshiba has engaged with Dongfang Environment. And together we have signed off a memorandum of understanding to look at possibilities how we may implement CCS into steel industry. And while we had this MOU arrangement, we had an opportunity to discuss with the Global CCS Institute, where they were looking for unique reports at the time for looking into several options for implementation of CCS projects into different arenas and different sectors. So we have proposed to the GCCSI whether we should do a feasibility study with their support in funding to do a feasibility study of applying CCS onto the steel industry in China. So this is really the background of how we have conducted this feasibility study. So once again, this feasibility study was done in a very close collaboration with the Dongfang Environment Company, and they were together did this feasibility study and wrap things up for us. So I would like to go into what we did on this project. It gets a little complicated maybe, but I will try to explain them fairly straightforward. So once again, it was Shogun Jintan, the company, who was looking to see options for CCS application into their steel plants. So we asked them which is the steel plant that you're interested in, and it turned out that they were interested in applying CCS into their South-Idian steel plant. And South-Idian is located 200 kilometers east of Beijing on the coastal industrial area. It used to be originally located around Beijing, but however, due to the Olympic Games, which happened at the time, they were relocated to the South-Idian area. It is a very large and modern steel plant, very large, and it is, at any rate, it is the subject of the feasibility study that we conducted. Now, once again, we come from the power systems company, so first we needed to understand what steelmaking was from scratch zero, but it was fairly straightforward it is a very, of course, very complicated process, starting from the raw materials to the final end product. But this is looking at it from the product perspective. We next dissected, also to say, try to understand the process as in terms of where the CO2 are and where for potentially carbon capture and storage can be applied onto these processes. So in the center of the steel making, it is of course the blast furnace, which melts the metal and so forth. And of course, we have other lime kilns and coke ovens and hot blood stove, all these apparatus that try to make the most economy out of the steel making process. And within all these processes comes the CO2 streams. Interestingly enough, I will get to this maybe later on, but we also have a power plant usually around the steel plant that of course pumps the energy to moving all the equipments in the steel plant. This also produces CO2. So we try to understand where the CO2 is, what are the things that's moving around, and where potentially we can apply carbon capture. The report gives you a more detailed outline, but this is really more or less a summary of what we did. So we first needed to look at where the CO2 emission sources are in the Shogun Jintan sulfide implant. And all these numbers in lime kilns, hot blast stove, coke oven, heating furnace, in-house thermal power plants. These were all candidates, so to say, of which streams do I want to pick out the CO2. In close discussion, once again, with the sulfide in Shogun Jintan, and also in collaboration with Tongfang Environment, it was decided that we wanted to first look at potential capture of CO2 from the lime kiln. This was really more or less a preference of the customer. Case 2, we decided, why don't we look at hot blast stove? Hot blast stove is a preheating of the air which goes into the blast furnace, which also emits a lot of CO2 as an intermediate process. We decided to look at this because of its high concentration of CO2 and, of course, very high volume of CO2 coming from it. As a power plant equipment supplier, Toshiba was, of course, naturally interested in looking at the in-house thermal power plants. But then again, of course, if I wanted to look at more or less the uniqueness of applying CO2 to steel industry, this would be more or less straightforward question. So for the purposes of the feasibility study, we looked very closely at case 1 and case 2 for the subject of the CO2 stream. We are all hopefully technology oriented. CCS, of course, comes with energy. We need to pump in some energy in order to recover CO2 from a flue gas stream. So next was identifying which heat sources we can use to separate the CO2 from these flue gases. We chose to use for case 1 and case 2 the hot blast furnace heat, which equates to more or less 440 tons per day worth of CO2 capture. And this was agreed to, once again, with the customer, Shogun Jintan. So next is a very simple schematic of what we did for both case 1 and case 2, which I have named here, lime kiln and hot blast stove cases. Case 1 being the lime kiln. Lime kiln case, we get the flue gas coming from the lime kiln, and we also, for purposes of feeding the CCS system with heat, we are utilizing hot blast stove furnace flue gas as a means to generate steam, which of course pumps into the CCS regeneration. The CO2 recovery rate was decided to be 300 tons per day. This rate was more or less a given. It was a preference and identified from our customer side that it's going to be 300 tons per day with a view to usage on the downstream, which I guess talk about later on. So lime kiln is the case 1. Hot blast stove is the case 2. So for hot blast stove case, we're utilizing the hot blast stove flue gas not only as a source for CO2, but also a source for heat. So if you look at the schematic on below, we are first diverting part of the hot blast stove gas into a steam generator, which of course cools, while generating steam, is cooling the flue gas down to a particular temperature level. Then we bring in the part of the flue gas into the CCS. So we're using 2 things from the hot blast stove, which is one CO2 and which is the second, the heat. So in order for the comparison, we did a 300 tons per day design for this particular case as well. One important item to point out here is that the CO2 concentrations are different for lime kiln and hot blast stove, the former being 19% and the latter being 29%. And the precursor, I just mentioned what we did on the Mikawa pilot plant. So our interest was seeing how these different flue gas CO2 concentration streams differ as in terms of performance and how the plant should be designed with these different CO2 concentrations. So using the modifications we put on to this pilot plant, we tested different performance, CO2 capture performance based on different CO2 concentrations. People know that higher CO2 concentrations will give you better CO2 recovery, which means lesser energy required for CO2 concentrations per ton. But we used our device, the pilot plant, to get the quantification evaluation for the effects and what needs to be put in as in terms of the plant design of the carbon capture. So using this data and together with the data, we first wanted to see where we should locate the carbon capture facility. The sulfide end plant is a very large modern plant built on the reclaimed land far away in the coastal area. So we had a fairly good liberty, so to say, as to choose because there was very little land limitations. But then again, still, we had to discuss and consult with our customers where we could potentially put the carbon capture facility. Out of the 3 locations that were identified, we chose to put or design the carbon capture facility at location 2, fairly close to the hot blast furnace. The reason being, first, of course, it's a proximity to the heat source. If we go away from the heat source, then we need to insulate all the piping for the steam and so forth. We thought it would be prudent to place the carbon capture facility near the sources of the heat. Of course, again, physically, location 2, there were little or less limitations on existing underground structures that we need to work on. So location 2 was chosen for the design. So for the same 300 tons per day capacity, we, based on the flue gas and how we bring in the flue gas as well as how we get the heat from the hot blast furnace, we did a design and costing of these plants for both case 1 and case 2. Case 1, as you can see, because of the large scale and where the location of the lime kiln, we have to divert the flue gas all the way across the steel plant, across 2,240 meters of piping to get the flue gas into our absorber. Well, once again, we put our facility very close or fairly close to the hot blast stove. We have a 680 meters piping that is feeding the flue gas in to get the energy to generate the steam here. We did the design and costing for the absorber, stripper, as well as compression stations around this facility. And this is the size and approximate parameters, as you can see on the slide. The second hot blast stove is there's no interaction with the lime kiln. So all we have to do here is get the flue gas from the hot blast stove, get the heat out of that, and then capture the CO2 from the detempered flue gas. So only the piping that we have to consider here is the 680 meter piping that's coming from the hot blast stove. So in summary, I guess compared to case 1, there are 2 things that need to be notified here. First being the equipment size. Case 1 and case 2 is different with the CO2 concentrations for cases. So because hot blast stove has a higher CO2 concentrations, the equipment tend to be smaller and of course more efficient. And number 2, this is a repetition of the former explanation I made. There's really no necessity to plan a long pipe and rack from the lime kiln for this case 1. So the capital expenditure that's associated with that is lesser for this case as well. In China, there really, of course, once again, there's no carbon price, no incentives as on the reduction of CO2 in itself. So what I did here was just run a very simple economics evaluations for these 2 cases. The capital cost, as shown here, lime kiln is $22.1 million US, and hot blast stove is $18.1 million US. We considered the operation of this plant for over 20 years at 8,000 hours per year operation. And what we did was, taking into the cost of utilities and operation maintenance, we inversely calculated the break-even price of CO2, which would make the project economically feasible. And doing that over the 20 years, I inversely calculate the CO2 price that would justify this sort of project. The lime kiln is calculated as 50.8 US dollars per ton of CO2. That would be the break-even price. And for hot blast stove, it's 43.1 US dollars per ton of CO2. I don't know how the audience may agree with me, but in terms of designing a CO2 cost at 300 tons per day, I think this is a fairly competitive price. Some of these prices can only be achieved with a 3,000 tons per day or something like that. But we thought that the price would somewhere much competitive, I guess, or maybe considerable when compared to other projects outside of China. At any rate, I guess I need to talk lastly about possible CO2 offtake and the reason why we chose 300 tons per day and so forth. There is the EOR candidate, which we're still approaching and discussing at the moment. It's a Chitong oil field, and we have reports that they're doing an EOR trials there. And from the Shogun Jintang carbon capture plant over to the EOR candidate site, there's a 40-kilometer route that needs to be taken. But because it's a reclaimed land, there's very little elevation from the source point to end point, which takes away the necessity for pumping stations in between. But at any rate, it is a possible offtake for this project when we should consider an EOR option to get this going. And in general information, as I put on the report, we have come to know that they're buying CO2 at 500 yuan per ton, which is about 80 US dollars per ton for the EOR trials there. So once again, if I compare the cost and what they're actually costing for the EOR trials, there's a possibility that, of course, this project can be made feasible. There are, of course, some outstanding issues that needs to be resolved. It's not all bright and everything. There are outstanding issues which I notify here. Further investigation may be necessary, taking into consideration variation in steel plant operation and flue gas composition. We're, of course, considering that everything is constant at the moment. Maybe we should look at the operational aspects. Detailed, careful planning of construction may be required so as not to disturb the normal production activity of the plant. I guess all the industrial plants are there not for the sake of CO2. So the detailed planning and construction maybe need to be outlined for further, so to say, comfort, I guess, for realizing this project. Further performance improvement may be sought through optimization and heat integration, although we tried to maximize the heat that's latent or there at the steel plant rather than creating a new energy source for that. Of course, there are still rooms for further performance improvement, which can be optimized through heat integration. Present proportion of CO2 capture is limited. Further scale-up design would require more investigation on imposed constraints. We're now looking at 300 tons per day. Can we do more? That of course, imposes more constraints onto the study and what we can do here. And of course, lastly and not least, further investigation clarification on CO2 offtake usage need to be conducted in order to match the source and sink, which is, of course, very important for all CCS projects that we embark on. So this will be my last slide, just a summary. So in the beginning, I just mentioned this is something new that we did for ourselves, but in summary, the concept of applying carbon capture technology to the Chinese and iron and steel industry has been illustrated. There are several options that we can embark on. Hopefully, this sheds some light into what can be done on a steel plant as in terms of carbon capture technology application. The study looked into matching of CO2 source and heat source of CO2 recovery at sulfide N, and two possible cases for carbon capture were identified. Both plant designs were developed and evaluated, so it's all in the report. Hopefully, if you have time, please look at them. We just took a very quick general cost evaluation on the plant designs developed. And I think it is maybe inherent to all the projects in China, the cost of capital is a little different from what we see here in Japan as well as maybe outside of Japan. But we find the cost of capital to be very different. And the uniqueness of the heat sources available in steel plant, we don't have to generate a source of heat. Maybe it's possible to utilize some of the heat. And therefore, the cost of CO2 capture is relatively competitive compared to that of similar sized projects in other countries and sectors. So with that, this is what we have done. And I am quite open to questions which may arise from this presentation or report. Thank you.
Thank you very much, Suzuki-san, for that excellent and informative presentation. I'd just like to remind everybody on the webinar that you can find the full report of this feasibility study on the Global CCS Institute's website, and I do encourage you to go to our website and read further details about this important study. From my perspective, this is a particularly important study because we know that the steel sector, not just in China but around the world, is a contributor to global CO2 emissions. And at this stage, there are limited, if no other, large-scale technology options for addressing those CO2 emissions other than carbon capture and storage. So personally, I think that this work conducted by Toshiba is incredibly valuable and will hopefully take forward the case for applying capture technology to iron and steel facilities around the world. And Suzuki-san, actually that flows neatly into the first of many questions that we've received about your presentation. The first question I have here is, how relevant do you think this feasibility study is to projects in the iron and steel sector outside of China? Or do you think that most of the lessons that you've learned here are really relevant mainly to a steel plant in China?
Oh, that is a very tough question, maybe from number one. But I think with respect to the steel industry, even here in Japan, this is not the only case that carbon capture is applied to a steel plant. To my understanding, I guess I need to pay respect to our Shin-Nippon Steel folks here in Japan who applied CCS for CCU in their steel plant. And they're also using post-combustion capture technology to my understanding, the hot blast stove, I think, CO2 emissions. I haven't talked to those guys in detail about that. I may be beating around the bush here, but my short answer is I think the study that I conducted here is quite relevant to all other steel industry or projects around the world. It is not limited to the case here in China. The process is quite similar, quite straightforward. You have multiple CO2 sources, different CO2 concentrations, and several heat sources that people want to maximize and optimize within the process. So it's quite, I think the study here hopefully shed some light into what can be done potentially to all other steel plants.
Well, that's great. Thanks for that. Now, I've got some more technical questions here about the actual study, so I might move into those. The first one is there a minimum temperature requirement for the heat source?
Heat source. Well, the heat source we looked at, we wanted to generate steam or saturated plus steam. So we have to, there are limitations on that. If we use a very low temperature flue gas, for instance, we need a larger volume. More or less, we can't have enough heat to supply the reboiler in a sense. So the temperature limitations will be imposed with how much steam we want to get out of the flue gas stream. So that would be the limitation.
Right. Okay. So the next question is actually about the thermal consumption. So I think you mentioned that the thermal consumption is 2.4 gigajoules per tonne at the pilot. Can you clarify what CO2 concentration you're referring to that equates with that thermal consumption, and whether there are any process optimization options been adopted, for example, intercooled absorber or split flows?
Oh, these are very tough questions, maybe coming from competitors.
I think we have some very keen and interested listeners on the line, Suzuki-san.
That's very encouraging. It's good to have a nice active audience.
Yeah.
2.4 gigajoules is the figure once again. If you may potentially go back to slide number 5 later on.
Sure, I'll do that for you.
It's working off a 90% CO2 capture at CO2 concentrations of approximately 12%. So this is fairly straightforward coal-fired thermal power plant flue gas. And yes, as I guess with common to many other technology developers in this arena, I guess I anticipate that we have here online today here. We do both things. One is, of course, get good aimings to give me this kind of low energy. And also, of course, heat optimization that matches the aiming solutions that we're adopting. So, and of course, I cannot really go into the details of what we do as in terms of heat integrations and so forth. But the short answer is, once again, is yes, we do those things in order to get 2.4. And we're also continuing to do these things as well in order to get this further lower. So once again, doing things on the aiming side and doing things on the heat integration side within the carbon capture facility to get this down. Yes.
Okay. All right. Thanks for that. All right. So sticking with the more technical questions here, what is the minimum CO2 concentration which could be captured from a steel plant?
Well, set aside the economics of anything. Once again, we've tested, if you're just looking at the same slide here, we had a different customer asking us to do carbon capture from natural gas combined cycle, what we can do on that. So that's down to 4% CO2 concentrations. We've done that. Lesser volume, but more energy is required to capture CO2 from a 4% flue gas stream. So theoretically, even if it's down to 1%, 2%, we can still adopt this technology to capture CO2, but whether that makes economic sense or not, that's a different story. But theoretically, we can do that. But I guess there are other potential ways to capture CO2 maybe, or some other economically feasible ways, but technically speaking, we can capture CO2 from even single-digit CO2 flue gas streams.
Okay, that's good to know. All right, so I did hear you mention in your presentation that the 300 tonnes per day recovery rate was in response to the customer's input. But the question I've got here is, do you think that was dictated by the enhanced oil requirements, or was it a technology requirement or barrier that dictated that recovery rate?
Well, in my understanding, with the discussion with the customer, it is more or less driven by the EOR demand at the time.
Right.
Not really the limitations on technology and so forth. With a great tribute to all these nice projects going around the world, as you know, Claire, we have 3,000 or 4,000 tons per day post-combustion capture already commercially available. So it's really not technology side. I guess it's more or less particular demand on the CO2 side that has dictated the 300 tons per day.
The 300 tons. Okay, great.
I can certainly look at other capture rates, but this is the capture rate that we worked to for this feasibility study.
For this study. Yeah. This could be a controversial question which you could avoid answering, but if it had been your choice, what recovery rate would you have chosen?
More the better, I guess.
Okay. Yep.
As there is always an economics of scale at play. the larger the scale becomes, the lesser cost of CO2 capture, meaning US dollars per ton of CO2. We know that by heart. So if we want to bring the economics closer, as long as we have a right consumers of the CO2, it's economically better to construct a larger plant rather than a smaller plant.
Okay, great. So now turning our minds back to the blast furnace, is there any modifications required or envisaged to the blast furnace, or because it's post-combustion capture, does that mean you can avoid making any modifications to the blast furnace?
Well, yeah, yes, we did talk about those things. Very briefly, not I guess into detail, but as you can see, all that sits beside the terminal point of the hot blast stove. After the hot blast stove is the stack. So we're just taking the CO2 flue gas stream off of the hot blast stove, and other than that, it's just going out of the stack. So there were, at least in the feasibility stage, there was really no discussion as to the limitations or some constraint that may be imposed about drawing the steam flue gas from the hot blast stove exit.
Right. Okay, so that might be something, for example, that you might look at if you were to progress to, front-end engineering design kind of thing.
Yeah. Well,
yeah.
Yes. If I look at it in power systems perspective, which I'm more or less educated in, I guess, there are some issues about drawing flue gas from our boiler, for instance, and sending it back, because post-combustion capture needs to cool it down to a certain temperature level in order for the chemical absorption to work, which means we have to send back the flue gas at a chilled temperature, lesser temperature, so to say. And usually the stack is designed to disperse the flue gas to a certain distance at a certain temperature. And if we are to make a modification on the flue gas going back into the stack, and if the temperature is lower, then there's some design changes that maybe need to be imposed on the stack, or maybe the gas heaters for the power system. So I'm envisioning that if we really go into details about that, we may have to discuss or maybe look into what we need to do on how we need to return the flue gas back into the stack. But unfortunately, we really didn't have time to go into that at this stage.
Yeah, sure. No, understand. All right. So the next question I have here is what's next for this project? Is there an appetite to progress to the feed study stage?
Yes. So that's what I'm working on right now at the moment. Hopefully that is the answer. But thanks to support of GCCSI, and we got the partners and right connections, hopefully now we need to present this over to our customer and hopefully get them interested. And it is also important, once again, to get a more solid definition of who the CO2 offtaker is. Maybe we somewhat ran out of time on that in terms of this feasibility study. So realizing the offtake and get more involvement or get more appetite or interest from the customer will be the first thing that we need to do on this project.
No, understand. All right. So moving just back to the technical side of the project, I've got a couple more questions. So the first one here is that the temperature of the hot blast stove flue gases seems quite high, and obviously very good for recovering heat. And the question is this applicable to other iron-making plants, or is it likely that you'd have to find other heat sources?
Well, it took us maybe an hour to 1 year to do this feasibility study, and of course we had to learn this by ourselves. To my understanding, I think the way the steel plant is designed, it's really different how they design all the energies. For this case, agree, the temperature is very high and it's quite much utilized. But I've maybe read in some some documentations or some other applications where they're, so to say, optimizing even further, regardless of CCS, how they use the energy out of the hot blast stove already. So what I mean is that they use the heat for different purposes other than carbon capture. So the heat is already consumed for other plants, so to say. So I'm not really good at answering all these questions in English, but I guess what I'm trying to say is, what I'm trying to say is, it's really different plant by plant. Agreed. I think the question is, hey, this doesn't really apply to my plant. Could be a case that may arise. For this particular Shogun self-IDM plant, we just happen to have a very good heat source, which is a hot blast stove, which we chose. But if I may look at other steel plants, they may have already optimized utilization of the heat for optimization of CO2 emissions and so forth. People do that for different plants, and if they've done that already, maybe we're limited on this option.
Which makes sense. You'd be competing with some other use for the heat, and that actually relates to another question that we've got, which is sort of quite similar, but is so you've obviously, the costs that you've got in this study and the system you've designed are all around a 300 tonne per day system recovery rate. So how do you envisage would the costs? Sorry, let me just get this question clear. So how would the costs increase if you were seeking a higher capture rate, particularly in regards to, obviously, you'd need more steam and heat?
Well, the way, maybe I didn't quite understand the question correctly, so I apologize if I don't answer this properly. One thing I must clarify is that the steam that we're utilizing is coming from the hot blast stove once again. So it was a heat to be thrown away anyway. So we put the steam generator right after the hot blast stove to get the steam. And we're not paying anything for that. The steam is just something that we got from this heat that was going to be thrown away anyway. So it is not in the equation of OPEX, operational expense for this project. So if I were to maybe scale up the project, for instance, and if we are to run out of steam, if we have to buy steam to a certain extent, of course, that will change the economics of this project. Maybe we have to look at some other different heat sources, so to say, that we can draw off from besides the hot blast stove to make it economical.
Yeah, no, that makes sense. All right, so a lot of the questions and comments coming in, Suzuki-san, are commenting on how are commenting on just how interesting this study is, and I tell you, it's not often that we get so many questions with our webinar, so I think that reinforces the point. But one question here is, if you look at the overall tonnage of CO2 from the site, what proportion would you capture through this project?
It's a very good question. We have, through the data that we receive from our customers, we try to calculate how much ton of CO2 is that is actually being emitted from self-IDN. It was one of the questions that we anticipated coming into this webinar itself. To our estimate, I don't have the customer saying or signing off to this yet, but it is, we approximately see about 40,000 tons plus of CO2 that's being emitted daily. 40,000. So out of 40,000, we're only doing 300, so that's about 1%.
Right. So okay.
That is, do I make things better, or should I go even larger? That is, of course, a case to be studied, I guess. But that is the proportion of things that we're doing here at the moment.
I see.
I think it's all dependent on how much ton of crude steel that's being produced for a particular site, and of course that with all the heat optimization that's done inherently, that really defines how much CO2 that's coming out of the steel plant. And I would anticipate that it's different, as with the power plant, how much CO2 is emitted for each steel plant. But I think the sheer magnitude of CO2 that's actually being emitted is far larger than what we're discussing here at the moment.
Yeah. Fair. Well, it is only a first step,
Yes.
and
Yes.
one of the questions we've got here is, well, do you have in mind what might be the most challenging or critical technical issues if you were looking to scale it up to a larger facility, more tonnes per day being recovered?
Well, the sulfide dam plant, if there is a steel guy here in this webinar, would may agree that it's located in a very large land and very small limitations on land and so forth. But if I were to go to a very big steel plant in this Tokyo metropolitan area, for instance, I know by heart that land is not available as much as what we see here. So one thing off my mind is that, of course, land limitation would be a very critical issue for constructing a very large scale carbon capture facility for a steel plant. And next thing, of course, would be, once again, the same drill that we did here. The larger the CO2, the more energy we need to put in. Where do I get my steam? Where do I get my heat? I need to match it with some other heat sources that's available in steel plants. So the larger the carbon capture gets, the more heat I need to draw from something. Do I have to make a dedicated heat source like a power systems? I don't know. Do I have to do that, or can I still draw from some other latent heat that's available in steel plants? So those are the things I guess we need to look into. More or less a challenge for the design of the CCS for those applications. So this is just an example, hopefully, and I agree that there are more the devil's in the details. I guess we need to look at all the finite things if we are to look at other power plant, steel plant applications.
No, I understand. So this one again this question might be beyond your current feasibility study, but do you have any idea of what the maintenance costs or might be involved with such a capture facility?
Well, we really, for the purposes of economics, we did put in an item called O&M, just in discussion with our partner, Tongfang Environment. We just put in a very simple operation maintenance cost. I guess I really didn't put in those figures up front on the report. But I do know that it's working off of the input that we got from our partner in China, as well as the things that we learned in our Mikawa pilot plant, where things were off and what the operational maintenance costs are incurred on the pilot plant and so forth. Those data are being utilized for cost assumption of the O&M for this project.
Okay, all right. Well, I think that might be a good opportunity for us just to remind everybody that the report is on the Institute's website. Hopefully in reading it, you'll be able to address many of the other questions that you still have about this project. However, if the report doesn't cover off those issues, please don't hesitate to contact us here at the Institute, and we'll be able to reach out to Suzuki-san and his colleagues at Toshiba to help fill in the details. On that note, I'd like to thank you again, Suzuki-san, for an incredibly informative presentation, again for an excellent piece of work, which I think is a great contribution to the work on CCS that's happening around the world. And I'd like to also thank all our participants for taking the time to listen to today's webinar and for sending in such excellent questions. I'm sorry that we didn't get a chance to get to all of them, but we'd be very happy to chat to you offline. Thank you so much, everybody, and have a good day. Thank you.